So good morning to everyone and happy Diwali to all. We are fortunate to have with us Professor Avinash Deshpande with us. Professor Avinash Deshpande is a well-known astrophysicist at the Raman Research Institute, and he's known for his contributions towards the studies of pulsar magnetospheric emissions regions and in the elucidation of unphysically ultra-dense neutral hydrogen irregularities in interstellar spaces. Avinash Deshpande, popularly known as Desh by all astrophysicists in and around India, has done his BTech degree from Indian Institute of Technology, Kanpur Institute. He did his doctoral research at Raman Research Institute, which he earned. He was awarded from the Indian Institute of Technology, Mumbai. Then he did a postdoctoral fellowship at the University of California during 1990-92. He's been involved in a number of projects undertaken by RRI. He's credited with the development of a receiver for high time resolution studies of pulsars at low radio frequencies. Professor Desh has been awarded the prestigious Shanti Swarup Bhatnagar Prize for Science and Technology, which is one of the highest Indian science awards for contributions to physical sciences in 2002. Today he is with us. He'll be having various sessions with us. Today he'll be talking about the fascinating lives, cosmic lighthouse.
Hello, I'm not able to hear you, Najam.
You can. Yeah, we can hear you. You can.
Oh, okay. All right.
Yeah, you can continue now. We have.
Oh, okay. Yeah, I didn't even notice because I lost audio.
Okay.
Okay. Good morning, you, and good afternoon or evening, based on where you are located. And happy Diwali to all. So it's a pleasure to be talking to an interested group. I've been told it's a very lively group. I also learned that Sushan has already talked to you about pulsars and neutron stars in reasonable depth. And today you might find what I'm going to say is largely what is already known to you, either even earlier or through Sushant's talks. This might be largely a repetition for both people who have heard our talks and are familiar with pulsars, as well as people who might have heard my talk earlier. So I apologize in advance for that. But let's see how far we can touch upon the same subject in a slightly different way, emphasizing different aspects. What I will be doing is I'll be highlighting in some particular color the aspects that can be best addressed through archival data. And you will notice that sprinkled across several slides. I will not elaborate on the aspect of that investigation just as yet, but I will point them out, and we will have chance to discuss those in greater detail in later sessions. So let me begin. I'm going to basically talk about radio pulsars. And as you already well know, that pulsars are these peculiar objects which give you pulse of light every rotation. Of course, it involves the essential aspect of rotation. There is also dynamo action. There is a huge amount of energy stored in this rotating object, both in terms of its rotational kinetic energy as well as magnetic energy. There is conversion of energy for us to finally see their presence and on the way to various other processes. These objects move in space at great speeds. They are great particle accelerators. There is, due to loss of energy, there is breaking of the rotation. There is interesting electrodynamics, which involves sparking across potential gaps. You will have the revolutions, both in terms of its spin as well as of other systems that are responsible for the emission that we see. And this emission and radiation at different emission of particles as well as radiation of electromagnetic waves is what we observe, and they are known to be great timekeepers, as you must have seen. So more than 50 years of observing or spying on them has been possible, except one would like to stress that almost all the information that we get from them, since we cannot see them in the manner that we see them in the images, the details that we learn about them are basically based on the information we have about them when we observe their intensity as a function of time. So that's the only access we have. Of course, we look at them in different colors or frequencies and also put that information together. Of course, as is well known, this story started in 1967 when Jocelyn Bell, a graduate student then, was using the Cambridge Radio Telescope to observe twinkling of stars, twinkling of distant radio objects. This is analogous to the twinkling that we see in optical. And that is what led to her allowing through the receiver a series of pulses of radio emission. Of course, the intensity goes high downward here at repeated intervals, which, as it turns out, is the period of the pulsar. And this periodic emission came through, and she doggedly pursued this to rule out all other local possibilities and establish that we are seeing signals of astronomical origin. One point that I often emphasize in this is that this is for the first time one ran the equipment with what is called short time constant. That means the system was responding to faster variations in intensity. More often than not, people preferred to run their equipment with longer integration time. That means slower variations alone were allowed, because one was looking for signals with whose intensity was not expected to change rapidly. And one also gained the benefit of making to be able to make more sensitive measurements. So of course, you have a less sensitive system when you have shorter integration or averaging of the data intensity. But it also allows now faster variations to come through. So this was opening of an unexplored parameter space till then, and it was richly rewarded by the signals, like the pulsar signals coming through. So this was, of course, the first evidence for periodic pulses, which were, of course, seen on the chart recorder. One didn't have the computers and so on like we have today. And of course, there was enough excitement relating to whether the signals were from extraterrestrial civilizations. And as more pulsars got discovered, it became clear that we are looking at a new class of astronomical objects. And as we know now that they are highly magnetized, fast rotating neutron stars. What is remarkable about pulsar discovery, as in similar to many other discoveries and conclusions, that very simple set of arguments, when put together, allowed people to zero on to the possibility that these are indeed rotating neutron stars. One of the first things was, of course, based on the sidereal time, which I'm purposely emphasizing this because as we will talk about different aspects that can be probed using archival data, these considerations will become very relevant. So the signals that Jocelyn was seeing was repeated its presence in the beam that was looking vertically up at an interval which was not exactly a solar day. It was a little shorter than that, and which can be also interpreted as a parallax measurement of sort because of Earth moving around the sun. The observer effectively was located at two different locations, well separated by the amount by which the Earth moved in a day. And the fact that the direction did not appear to change meant that we are looking at a very distant source, well outside the solar system. The small pulse width that one saw also implied something very profound. If something lasts for a short time and switches off, that sets a limit on the size of the source by the simple argument of what is called the light travel time argument. So the speed of light times the pulse width sets a sort of upper limit on the physical size of the source, which is lit and switched off. And so that meant that these are very compact objects. It gave a size which was of the order of thousands of kilometers. And people, of course, considered that time well-known, and even today, a well-known case of pulsating stars which produce periodic intensity variations, like Cepheid variables. But there the period is proportional to some power of density. And already one had seen a period range which was about at least factor of 4 by then. And that meant almost an order of magnitude or more than an order of magnitude range in the densities. And that is somewhat unlikely for a single class of objects. Now, the amount of emission that one saw, and if you work out the rate at which the energy was being lost, you can, that is from the slowdown of the pulsar, you can immediately calculate what is this, get a sense of the reservoir of energy that the object has. And you then saw that fact that it is a very compact object, and that combined with the stability and shortness of the period, you concluded that it must be a massive object. The shortness of the period implied high density, and you already know the size limit And you also need a big flywheel, which is not slowing down rapidly, even after emitting the kind of energy that we see received by us. So just these four arguments, or three arguments implied together, when used together, ruled out almost all the possibilities except white dwarfs and neutron stars. And of course, the white dwarf possibility was ruled out very readily when one discovered a pulsar in the Crab Nebula, which was rotating pretty fast, faster than what white dwarf could rotate. And so that, basically zeroed us down to the neutron stars, about which you heard a whole lot, and also that these are born typically in the process that amounts to death of a normal massive star. And these were interestingly predicted by Bade and Zwicky in their conjecture when they were talking about supernova explosions, and this being as an end product, compact end product of the explosion. So in this rest of the talk, we'll be talking more about the rotation powered pulsars and more of their radio properties and what we can learn from what we have observed in the last 50 plus years. Okay, so this is the discovery that I was mentioning, and this actually happened in optical. Here you can see 1 millisecond exposure photographs of that small region zoomed into, showing a persistent emission from one of the objects here, and the other object appears and then disappears and reappears and disappears over the cycle of 33 milliseconds. And this was relatable to the supernova explosion, this object and its location and association with the Crab Nebula, with the explosion of 1054 AD, which was documented very well by the Chinese astronomers. So, so these are the kind of mentions I will be making in Mao color on various transparencies or various slides, and which we will have chance to discuss later, how we learn about this using archival data. All right. So, of course, these are remains of massive stars, but the range of massive stars that are progenitors of pulsars or neutron stars is believed to be in the range of 7 to 20 solar masses. Of course, prior to the explosion, they would have lost a large fraction of their mass through the wind and so on. And the final remnant mass is, of course, pretty close to 1.4 solar masses. Of course, it has been also seen that it can be higher than that and can be as much as 3 solar masses. Of course, this is tied up with the famous celebrated Chandrasekhar mass limit for white dwarfs. And so, and this has been borne out by the data that or inferences about the mass people have made through various binaries that people have observed. Okay, I'm not going to spend much time discussing the structure of the neutron stars. You have been told about it in much greater detail, except to say that there is superfluid superconducting core and the coupling between the core and the outer crust is actually the interest of several people, and that is something that can be probed through the behavior that we see of pulsars in time, particularly in terms of the way they slow down. They show Earth, I mean, star quakes, equivalent to star quakes. People have also talked about plate tectonics and so on in the context of. We will touch upon this a little later in slightly more detail. But in any case, we are looking at a very dense object, densities reaching to very high values, particularly at the inner core, which might contain other material or other forms of material like quarks and so on. All right. Now, the energetics involved in a supernova explosion is, of course, the extreme type. When the core implodes, the released released potential energy is what gives the kinetic energy to the outer envelope, which is thrown out and makes a beautiful circular or spherical remnant, which expands into the space there, in the ambient medium there. And its morphology is largely dictated by what is around and how the expansion is allowed, symmetrically or otherwise. And the imploded compact remnant, of course, is this object that we are interested in. Now, because of the size reduction of the core that imploded, people can expect quite independently high magnetic field if the progenitor had certain field, like let's say 100 Gauss or something. There will be amplification of 10 orders of magnitude, given the 5 orders of magnitude reduction in the radius from, let's say, 1 million kilometer to about 10 kilometers. And one can land up with high strengths of magnetic fields on the surface of this new star of the order of 10 to the 12 Gauss or so. Similarly, the higher rotation speeds, people believe, would also come from conservation of angular momentum. If the core was rotating at certain speed, you will have the ballerina effect, and you would get the compact object rotating correspondingly faster. Again, similar reduction in the similar order reduction in the moment of inertia, and similar order increase in the rotational speed. Okay, except the difficulty is in that was noticed pretty soon that the cores were not seen to be rotating that fast or fast enough, and they may or may not have as much magnetic field that one assumed, like typically 100 Gauss or something like that. And so one was groping for, the explanation for this high spin rate of the pulsars at birth. One has also seen the pulsars moving at very high speeds through the space. That was also something that needed an explanation, and a common origin of spin and space motion was proposed, which can be very well described as a simple off-center kick. As you kick a football, for example, when you kick it at the center, you will find the football moving in the direction of the kick. Whereas if the kick is off-center, you will get the motion of the football, as well as you will see the football is spinning around a certain axis. Of course, this kick is imparted effectively by the recoil due to asymmetric emission of neutrinos, which carry most of the energy at the time of the explosion. And it can also come from asymmetric supernova explosion. But the amount of asymmetry required is so tiny that it can be produced very easily. So this was proposed as a mechanism which has been pretty successful in explaining both the high rate of spin as well as high speeds at which pulsars are seen moving through the interstellar space. Now, if this were to be true, of course, the analogy that I just gave, it was very clear that then the velocity, the direction of motion of the football has to be perpendicular to the axis of the spin of the football. And of course, verification of this requires, taking an ensemble of objects, and the data on young pulsars seem to support this. Apparently, data on older pulsars don't support this as well. But you will find that this support is pretty overwhelming, and maybe the pulsars forget their original direction of motion due to a variety of things that happen later in their life, even if there is no evolution of the spin axis. So that's an interesting aspect which one can explore using archival data and so on and so forth. But what is, of course, not known yet and which needs further investigation is what is the duration of the kick, which we'll, of course, not know unless we see these things in action. But one can produce models and see how the sensitivity to duration of the kick would manifest in the way they are seen in terms of the orientation of the spin axis and the velocity and so on and so forth. So all that needs to be clarified still, and there is continued interest in researching on this. Of course, as I said, these objects move at very high speed through the interstellar space, and the speeds are well above the local sound speed in that medium, and they produce a shock region like what is seen here. They produce bow shocks in front of their location, and also structure that might still be visible based on the memory of their presence or passage through the space. And beautiful examples are seen. One such is shown here, which is called the Guitar Nebula, sort of apparent from the shape of this nebula. This is the shape that one is referring to. So this can be seen in H-alpha imaging, which are done with very sensitive telescopes. And you can, sort of know the position of the pulsar, and the association leads you to a lot of information about the way both the motion manifests itself this interaction with the interstellar medium, what it leads to, and what that gives you about information about the properties of the medium, in addition to what the pulsar itself might be doing in terms of immediate surrounding around its present location. We'll see examples of that as well. But coming back to pulsars and how they radiate, of course, the basic lighthouse model that where we have a source of light in rotation, and much like the lighthouse. And we see a pulse every rotation. That was proposed as a basic model by Tommy Gold and Franco Pacini almost soon after the discovery of pulsars. And that has remained as the key process through which we get the periodic pulsation. But what produces the radiation that we see was not very clear, and its association with the magnetic poles or action in the magnetospheres of the pulsars was became clear only after the famous observations of the polarization of this light that Radhakrishnan and Cook made using the Parkes telescope. And as you can see, let me get the cursor here. What they observed is close to very high degree of linear polarization with pretty well-defined rotation of the plane of polarization across the pulse as one went through the cone of radiation that repeats period after period. Now, it turns out that this exact S shape depends on the magnetic axis orientation and the way the observer is located with respect to this system of magnetic axis and rotation axis. So this is called the magnetic pole model, where for the first time one realized that this is indeed coming from the magnetic pole of the star. So the change in the plane of polarization, which is nothing but the plane in which the electric vector of the electromagnetic radiation is seen to oscillate preferentially, is was understood as a certain magnetic field structure in this cone that sweeps past us each time we get a pulse. And one can think of the observer sampling different parts of this region through as the rotation continues. And as you can see, these are the magnetic field lines for a dipole magnetic field. When you look down the pole, will look like in projection, they will look like spokes on a wheel. And the orientation of the spokes is, of course, changing systematically as we sample through this cone at some offset. Here also, of course, centrally also, if you change, if you go through it, it will also change, but it will change dramatically from this orientation to the opposite orientation suddenly when you cross the center. So there is a lot of information people have been extracting from this study of the polarization position angle sweep, as it's called, and many of these measurements are available now freely in terms of average properties, polarization properties of a large number of pulsars, and there is a lot to be learned there. What this polarization position angle sweep indicated, in addition to the details of the viewing geometry, as it's called, is the high degree of polarization.
Desh, I think your net is gone. Desh, you got muted. Yeah, he's gone. Just be on the line. I think there's a problem at the speaker's end. So just stay online. If there are questions, you can type in the chat. We'll just get in touch with the speaker. Yeah, just be patient. Desh is trying to reconnect. There's some internet issue there. He'll be back with us soon.
Hello, am I audible now?
Yes, sir, you're
Hello.
audible.
Okay. All right. So
Yeah, we can hear you.
Okay. Yeah. Sorry for this. It's a very frustrating
No
dropping of the
problem.
line. Okay. So I will try to reshare the screen and continue from
Yeah.
there. Okay. All right.
Yeah, we can see your screen.
Okay. Let me see if I can change it to the slideshow. Right. Okay. I think this is where we were. So, with due apologies, let me continue. So we were talking about this high degree of linear polarization that one observed in the case of this particular object, and later, of course, in other pulsars as well. And it basically implied that there is almost one-to-one association with the location of the charged particle and the polarization it would show will be tied up with the structure of the magnetic field at that location, which also meant that the particles are not radiating in a very wide cone, because had they been, you would have had mixing of polarization states from radiation received from charges from other field lines nearing it. So it was clear that we are seeing beamed radiation from highly beamed radiation from individual particles, which means their Lorentz factors are very high, and the cone width is then dictated by 1 upon that factor, and which explained why we see high degree of linear polarization, and that the charged particles are moving strictly along the field lines like beads on a string, because if they try to move away, the transverse momentum is instantly radiated away. And so that's the overall picture. And large number of such particles radiating together must be giving rise to the high brightness one saw, and coherence in radiation was already implied by the fact that you are seeing high degree of polarization, which cannot come unless you have high degree of coherence, because if whatever decoherence will amount to depolarization as well. But quite independently, based on the intensity level itself, one concluded that such a high brightness is required for us to see the amount of radiation we see at a distance of the object. Okay, so it was clear that we have fast rotating, highly magnetized neutron stars with very clearly defined spin axis and an arbitrarily inclined magnetic axis with largely dipolar morphology. And we are seeing the radiation coming from the cones associated with the magnetic field and beaming along its axis. So rest of it is just additional information which you know about, which gives you the range of masses of the objects and radii and the fields and the periods. But something that is not realized and never talked about is that pulsars are actually one of the lowest frequency emitters of intense radio radiation. They emit radiation at a very, very low frequency. And how low? It's really the spin frequency of the pulsar associated with the pulsar rotation. So if the pulsar is rotating at, let's say, period of p, then 1 upon p, which is the repetition frequency is actually the frequency at which the largest amount of electromagnetic radiation is given out from the pulsar. Okay, that's the dipole radiation, magnetic dipole radiation. And that radiation is actually the major accounts for the major energy loss, which comes at the expense of the kinetic energy, rotational kinetic energy of the pulsar. Except that this intense radiation cannot travel very far because the interstellar medium has material in it, and that interacts with the radiation, and the charged particles there will not allow radiation below a certain frequency to pass through, to either get absorbed or reflected. And that frequency for the interstellar medium is of the order of a few kilohertz, and pretty much like our ionosphere has this plasma frequency of in the range of 3 to 10 megahertz, because of which we don't receive radiation at frequencies lower than this cutoff frequency. But what happens is this radiation, which cannot get out very far from the pulsar, has both energy and momentum, and it pushes the surrounding medium, what you can describe as radiation pressure, and the ramp pressure of the material that is trying to push against will balance at some level, and that results in a formation of a cavity around pulsars, which have been talked about by Reason Gun in great detail. And this is something that we will touch upon again in some other context pretty soon. But what reaches us is not this radiation at the very low frequency. What we see is some manifestation of the action in the magnetosphere relating to this rotation and the presence of intense magnetic fields. And it produces radiation that we see, which is typically below 1 gigahertz, and is seen to have non-thermal spectrum, which means higher intensity at lower frequencies. So the main radiation that is coming out of pulsar electromagnetic radiation is not what we see. What we see is not really responsible for the major part of the energy loss that the pulsar undergoes. So as I mentioned, we have this magnetic dipole radiation, which is the main energy loss mechanism. We can calculate at what rate the energy will be lost due to, if we had a magnetic dipole radiation, and if it came from rotational energy loss, then we can tie it up together and use that to estimate, in fact, the strength of the magnetic field, which is what people do, in which, other than these factors associated with the pulsar, the moment of inertia and the radius, the measurable entities here are readily measurable entities are simply the period and the rate of change of period. So by using these two numbers, which people routinely measure for a given pulsar when they observe it, people have been estimating the strength of the magnetic fields, and that's what we refer to when we say this pulsar has so many Gauss magnetic field, and so on. So one can also estimate the age, characteristic age, which Sushant must have mentioned, assuming this being the same energy loss mechanism, and that the pulsar is born with a very short period, and then the rate of change of period is also evolving since its birth. If you take all that into account, you can get a rough idea of the age by dividing the period divided by twice the rate of change of period. and people have been using these numbers effectively. And this is also something which will be relevant when we talk of archival data. So the general picture is that you have this radiation which comes at the expense of rotational energy that will cause the pulsar to slow down in rotation, and if anything depends on the rotation, all those actions will be affected. And the important one there is the dynamo action that it has. Basically, a rotating magnet will generate electric field and a large amount of potential difference, which we will come to in the next slide. But before that, as pulsars are supposed to be slowing down gradually, monotonically, they suddenly undergo sudden changes in their rotation rate. Sometimes the rotation rate increases momentarily, which means a sudden drop in the period, and then it continues to evolve pretty much the same way, but might be with a slightly offset track. Now, these changes in sudden changes in the period are seen in large number of pulsars, not all of them, and these are called glitches, which Sushan has talked about in great detail. They can be pretty large as a fractional change, part in a million to a few parts in a billion. And there is a lot of exotic physics involved in the way the glitch occurs, the time scales over the glitch occurs, and the recovery in the period that one sees. All that, although shown as a small step here, has a lot of detail. And when you zoom onto it, and people have studied that. Since we talk about this analogous to earthquakes and so on, and there is understandable continued interest in knowing if one can predict such quakes, similar questions can be asked in the context of pulsar as well. Is it possible to predict when the next glitch will occur? And interestingly, the answer seems to be yes. And in fact, there is a beautiful demonstration of a particular pulsar case where it has been possible to predict it with the uncertainty of less than a week. We can talk about it later when we discuss opportunities of using the archival data to study some of these aspects. Okay. Oh, my video is off, so let me start it in case, as long as it doesn't cause the connection drop. Let's see. All right. So Sushan must have talked about this a great deal. So when the pulsars, die, when the dynamo becomes weak, we have them crossing this, what can be loosely described as a death line, which is shown by, indicated by this red band here. So they evolve, they're born with certain period and magnetic field, and during their lifetime, which might range from a few million years to a few tens of million years, they may not change the magnetic field strength, but will slowly slow down, and the dynamo becomes weak enough that they cannot do the needful action to produce the radio radiation, and so they die as radio pulsars. We stop seeing them because they're not bright enough in radio to be seen. And then based on their life history, which is greatly influenced by whether they have a companion or not, they can returned back to life, or they can be brought back to life by a willing companion. If the companion is willing to help immediately, they can come here. If it takes a long time for the companion to be ready to help in terms of giving matter which can be accreted by this compact star, and the angular momentum can be received from the orbital angular momentum, and the pulsar can spin up. If this happens much later, by then, if the magnetic field has reduced due to whatever reasons, then it will appear somewhere here. And the famous case of millisecond pulsars, where the companion takes really, really long time, being a low mass star, to evolve and be ready to accrete the matter. Magnetic field would have dropped significantly by orders of magnitude, and then the pulsar, even after spinning up, lands up in this corner with very low magnetic field, but now can be spun up to very high spin rate, which is what makes them the millisecond pulsars. So all this you have seen, and Sushant must have illustrated also how one has learned about this from connections, evolutionary connections that have been inferred based on collection of data on large number of pulsars, which is again as if using archival data. So it turns out that most pulsars are born in binaries, so the chances of their getting back to second life are not very dim. Even this is based on population studies and kind of inferences you can revisit by using the archival data. I will not go through details of this because Sushant must have done a very good job of it. The essential aspect here is a variety of scenarios are given. Even if you have a binary companion, it's not clear that you will actually have it available to you to make your return next time again in the pulsar island after having died once. And that depends on whether the binary survives in various stages of explosions or disruptions that can be caused by energetic events like supernova explosions. But what was remarkable is the discovery of millisecond pulsars when it happened in 1982, where the pulsar was seen to rotate at a very ultra high speed and seen to have very low magnetic field. This was seen as an isolated pulsar. But Radhakrishnan and Srinivasan put forward this point that even if it is seen as an isolated pulsar today, for it to be the way it is right now as high rate spin and low magnetic field, it must have had a binary history. And this is now confirmed through large number of low mass X-ray binaries that are studied both in X-rays as well as in radio as end products of that system as millisecond pulsars, which are large fraction of them are seen in binary systems where the second explosion has not disrupted the binary. There is, of course, formal research in binary pulsars, and the first such binary pulsar was seen or detected, discovered from Arecibo telescope in 1974 by Hulse and Taylor, and you know the full story about it in terms of it being a relativistic binary has helped us in confirming several predictions of the general relativity. The famous observation of the precession of perihestron has the shift of periastron is the first level indication of the orbit evolution, and the orbit also precises due to geodetic precession, which is also observed, and it's pretty substantial. It's 4 degrees per year, and so there is a lot of excitement and learning that has happened through this pulsar, which of course this famous plot is associated with the great finding, which of course was awarded duly the Nobel Prize in 1993. But we also have a new lab now, which is a double pulsar, where both the neutron stars are acting as radio pulsars, and this is even more exciting system where you are able to resolve certain ambiguities that are there when you are not able to measure the orbit and evolution of the second object. So things like inclination and so on of the orbit are readily determinable, and large number of otherwise undoable GR tests are now possible. Except that the second pulsar is undergoing geodetic precession, and that has caused the pulsar to be not visible for many years now, and people are eagerly waiting for it to reappear. So if people are monitoring this pulsar, a keen eye is required to see when it reappears. All right, we have already been told that millisecond pulsars are ultra-stable clocks, and that property of theirs is being exploited other than using them as clocks otherwise, in also using them, a bunch of them, as a timing array to possibly try to detect gravitational waves. And the idea is that their apparent locations will undergo changes when gravitational wave passes, understood in terms of curvature of space-time, and that will affect the arrival times of the pulses we get from these pulsars, and based on correlated variations that one will see in different objects in different locations, one might be able to infer presence of gravitational waves. Now, I think I will probably halt here and see if there are any questions, because we can cover this other aspect and talk about it later in another session. So is it a good time to stop and...
Just perfectly. So if there are any questions, please unmute yourselves and ask, or put it up in the chat window.
Hi, Desh.
Hi.
I have a so as you suggest that the asymmetric neutron emission or the asymmetric explosion happened during the supernova may cause fast rotation of pulsar. My question is it always the case that there is an asymmetric emission for which this fast rotation happens, or there are different kind of models?
Yeah, the asymmetric neutrino emission or asymmetries in the explosion, the exact reason or combination of it is not cannot be stated with any greater certainty because of you do not have any way of knowing it. the details or measuring those details. But people have talked about neutrino oscillations, which are influenced by the presence of magnetic field, which imprints the first level of deviation from spherical symmetry, as you can see. And so it's not very unlikely that such asymmetries are readily plausible. Now one can ask, what is the level of asymmetry that is required? And it turns out that given the energetics in the supernova explosion and the amount of energies carried by the neutrinos, the energy required to set this heavy object in motion with high space velocities is not really a large fraction of that entire energetics. So it seems really likely that this is rather easily produced, this level of asymmetries. In fact, it will be very hard to keep something very spherically symmetric in given all the reasons for possible deviations from the symmetry, even including the surrounding and so on.
So is there any evidence detected from the neutrino detectors, evidence of this asymmetric neutrino emission, or can there be any evidence in future?
You wouldn't know. You're getting neutrinos only in the direction that you are at, unless you have ways of measuring the neutrino emission going in other directions, which manifests in certain ways. You cannot infer about the level of asymmetry or symmetry.
Yes. Okay. Thank you.
Should be asymmetry, right? Unless
Pardon?
you have, I said the default assumption should be asymmetry. Obviously.
Correct.
Yeah. Okay.
You will require a lot of effort to maintain symmetry.
I know, because generally the simplistic picture we have in our mind is always a symmetrical one, right? Which is obviously a bit too simplistic, right?
No, which is okay for doing quick calculations and so on. And here, with the level of asymmetry one is talking about is really tiny, a part in an 1,000 or something like that, which would come due to a variety of reasons.
There's another question by Gitanjali Sethi. Are glitches repeated?
Yes, there are pulsars where glitches are given out at intervals which are not very long. Sometimes once in a couple of years is sometimes within a few months, and so on and so forth. And the remarkable thing is that there are prolific glitches like the Vela pulsar, which give very large size glitches. That means their period changes by an amount which is a few times, okay, warning me about the, so I'll stop my video. All right. What I was saying is the glitch sizes are pretty large in terms of fractional magnitude in the case of Vela pulsar. There are pulsars which glitch, and the amount of energy, the amount of relaxation in the stresses that would have built up, which would have resulted in the glitch, decides when the next glitch will occur. It's like the analogy I give is of a bucket. When it fills to the brim, you get a glitch. Let's say that time you empty it arbitrarily, and the amount by amount that you have emptied decides when the bucket will fill, how long the bucket will fill to the brim again. And this kind of a picture is relating to, of course, the fact that the interior core is rotating at certain speed, and that being superfluid, as the outer crust slows down with the loss of rotational energy, that they're not keeping up with each other, and that differential rotation is what builds up the stresses in the coupling region between the crust and the core. And it's like a rubber band. At some stage, it says, okay, enough of differential rotation, enough of the amount of differential winding that has built up. Let's relax it now, and let's share the angular momenta. And when that happens, you get a glitch. And for that to happen, if there is a threshold value of stresses, then the kind of behavior one sees in pulsars is actually readily explainable. And this exact thing has been seen, was suspected for a long time, but there are beautiful demonstrating pulsars. One of them, in fact, as I mentioned, where we can almost predict when the next glitch will occur. By knowing how much it relaxed now, we know the rate at which the stresses are building up and how long it will take to rebuild the stresses to the threshold value. So yes, there are a large number of repeating glitchers.
There are two more questions. Sargam asks, what reason is responsible for fast rotation of pulsars? Is it magnetic fields which rotates them fast, or other factors involved?
Well, the rotation has to come as you know, at the birth, or later if somebody pats it in a certain way, which is like the accretion helped spin up that we see in the binaries when the pulsars are brought back to life from having slowed down. They are spun up by the accretion, where the matter carries the angular momentum, the orbital angular momentum. And so that time, if they're rotating, if the original rotation was along some other axis, you will find that this accretion will, when it overwhelms in the contribution, it will set the pulsar rotating with the spin axis perpendicular to the orbital plane. But otherwise, the spin is really what they are born with at the birth. And that might be tied up with the asymmetry and the, like the football kick that we were mentioning, or simple ballerina effect of slow rotation of the core, now enhanced by this factor of almost 10 to the 10 when the moment of inertia decreases. Does that answer your question, or have I missed the sense of your question?
Yeah, I suppose so. Avik Das Gupta asks, are there any polarizations other than linear seen in case of pulsars?
Yeah, of course. You see, let me go back to that plot. If it, I think it shows. Okay, so if you look at this, profile, don't worry about the details of whether it's a single component or double component profile. What is shown here in the other dotted curve is, which is now almost looking like a continuous thing. The other profile, the slightly lower intensity profile, is the amount of linear polarization. And the other broken line here below is what is showing the amount of circular polarization. So in principle, we see high degree of polarization, that is certain. The polarization state might be describable by an arbitrary ellipse, where the linear component of it does this dance of the S shape. And the circular polarization also might change across the pulse, which might even change the sign, the handedness of it, and so on. So yes, in principle, we get, in general, elliptical polarization, which can be thought of as a superposition of circular and linear. And we can get significant amount of circular polarization at times. Sometimes 100% circular is also seen on the short time scales. But on long time scales, the average effect of linear polarization dominates, and there is not as much circular polarization as is seen. Of course, it all depends on the geometry of your viewing and so on and so forth. There are suspicions that some amount of circular polarization might be produced outside the pulsar region. There's no particular support or confirmation or elaborate theory for it as yet.
There's one more question from SK. Where do we mostly find pulsars in a galaxy? Any specific preferred region?
Yeah, they at the birth, of course, they are like the infants. They are in their houses where they are born, where their parents are, and that is the location where the sociology of massive stars takes them, and that's largely the well in the plane of the galaxy and along the spiral arms where associations of massive stars are typically found. So that's where they are born. But thanks to the speed or the kick that they receive at the birth, the natal kick, they also are seen way away from their birthplace at later times, based on how long it has been since their birth and how fast they have migrated away from the birth location. So yes, their distribution across the galaxy, in the galactic, with the volume of our galaxy, is of great interest, and this is something that I would be referring to as one of the issues that one can probe using the archival data. And it has got lots of interesting implications.
There's a question from Namrata. What are intermittent pulsars? Are they different from nulling pulsars?
They are nulling pulsars with, in fact, I didn't get a chance to, we will be talking about this. Let me just flash that transparency, which I'm sure Sushant must have described in great depth. But this is my favorite piece of evidence that has come in the recent time. So I think it's also called by others a part-time pulsar, which is a beautiful observation done by Kramer and collaborators in 2006, where a pulsar was seen to be active as radio pulsar for a few weeks, and then for several weeks it was not radiating in radio, which can also be understood or described as long duration nulls. Now, if this is probably happening on different time scales and with different gaps without any particular periodicity in large number of pulsars. But what was remarkable about this observation is that one could actually begin to see different behavior of slowdown in these different phases of active and inactive. And we will see the implications of it later in our discussion. But yes, the intermittent pulsars and the nullars are probably manifestations of the same phenomena of nulling. There is also a possibility that the intermittent pulsars may also be additionally affected by the fact that coherent emission requires, this huge amplification factor that coming from coherence of large number of particles radiating together. If a distant pulsar, which is not otherwise visible, is visible once in a while when the coherence level is high, you will find the coherence level itself can change, and that might lead to intensity variations, which are pretty natural. You've seen such cases even in the crab pulsar, where giant pulses are seen with large number of intensity variation. And as can be expected, more intense pulses come rarely, or more rarely. And so intermittent pulsars could be just that, a few pulses, strong pulses, because they are visible. It's not that they've stopped the radio radiation, but because they are so far that we can see only the tip of the iceberg, as they say. So they can be combinations of both intensity variations, making them appear as intermittent, because they're visible only when they're ultra bright, or completely switching off of the system, power failures or breakdowns like the nulling. Does that answer your question?
All of you can unmute yourself.
Yeah, if someone wants to ask, they can unmute and ask, or they can, yeah.
Sir?
Yeah.
Sir, I have a question. Can we use gravitational Poisson equation in the hydrostatic approach for the pulsars? Because I know for compact objects, compact astrophysical objects, since they have relativistic effect, we cannot use Poisson's equation, the Newtonian approach, Newtonian gravity approach. But in case of pulsars, is it possible or is it the same?
You mean in terms of how their interior is?
Yes, sir.
What is the equation of state and so on? Of course, I think all the relativistic effects are taken into account.
If we consider the relativistic effects, then Newtonian gravity approach or the Poisson's equations in Newtonian term is not possible. But I read somewhere that for yes, sir.
Yeah, go ahead.
I read somewhere that for white dwarfs and neutron stars, since they are not that much compact and astrophysical objects, so we can use gravitational, the normal Poisson's equation. But I'm not sure about pulsars. That's my question. Is it the same for pulsars? Or?
Yeah, pulsars are neutron stars. So I think what you just gave the answer yourself. If the discrepancy in the two approaches is not very large, because neutron stars are not that compact, and one can still use the Newtonian description, it is relevant for pulsar as well, really, because pulsars are neutron stars.
Okay, I got
it. I have one more question.
Yeah, go ahead.
The energy loss mechanism, you mostly refer the electromagnetic energy loss, but my question is, isn't the gravitational energy loss through gravitational wave is more or dominating?
No, I mean, if it's a nice spherical object, right? And it's rotating with, its symmetry axis. If the spin axis is one of the symmetry axis, then, even if it's oblate spheroid or slightly distorted shape from the spherical thing, it will not radiate gravitational waves. But yes, there could be mountains on it. There could be offsets in the of the spin axis from the symmetry axis, and that might lead to wobbling and lead to precession, free precession, and so on and so forth, and that might lead to radiation of gravitational waves, but that's not going to be a huge lot, as in the case of a coalescing binary signature that you will see a pretty loud signature of this radiation. But there is significant amount of energy loss coming from the particles that are lost from the particle flow that is associated with the pulsar cones. We'll talk about it in the next session. And so that's a major energy loss mechanism which was not yet incorporated very well, and it's tied up with this story of the part-time pulsar that I was mentioning.
Okay, those particles are the charged particles and neutrinos. Are you talking about that?
No. Neutrinos that I mentioned were relevant as major energy carriers only at the time of the explosion.
Okay, thank you.
There is no significant neutrino radiation later in their life as they work as pulsars.
Here's a question from Avik Das Gupta. Thank you for explaining polarizations. How will the ISM affect the polarization seen by us?
Yeah, actually it affects it a great deal, and it is something that we use profitably to study the medium itself, as much as the dispersion effects are relevant, which you must have heard about, where the different frequency radiations travel with different group velocities through the medium. The group velocity, if you like, if you want to treat it that way, continue that description, you can think of it as a group velocity being different for different handedness of circular polarization. And that will delay different handedness radiation differently, and that will that will manifest itself in terms of rotation of the plane of polarization of the linear component. And so the polarization plane as the signals travel through magneto-ionic. So you will see what is called Faraday rotation medium, where the component of the magnetic field along the line of sight becomes most relevant. And of course, the strength of electron density that you have. And it typically turns out that using this Faraday rotation measurements, which of course the amount of rotation will be frequency dependent, much like the delay relevant in the dispersion. And so by measuring the differential rotation across frequency, one can infer the amount of magneto-ionic matter that the signals have encountered. And that comes out to be a simple product of dispersion measure and the magnetic field, line of sight component of the magnetic field. People have used this profitably. They call it rotation measure, like the dispersion, analogous to dispersion measure, which refers to only the delay in arrival times, and have used this to infer magnetic fields within our galaxy. So yes, the signals are affected by the passage through the intervening medium if in the presence of magnetic field. And we have used this profitably to probe the magnetic field in our galaxy or anywhere else where the propagation is taking place through the magnetoionic medium.
So thank you, Desh. I think there are no more questions. So
Okay,
let's thank
so
Desh.
Yeah. And to let everyone know, we're going to meet Desh again, so you can still think of questions.
There are more sessions with Desh. One, and then the Saturday after that too.
I'll put it up on the list.
Yeah. So thanks a lot, Desh, and happy Diwali to all of you.
oh yeah, thanks to everyone joining even despite the pressures of Diwali celebration, and wish you all a very happy Diwali as well as New Year that begins for many people from within a few days.
I think it's Monday. It's Monday.
I see. Okay, right. Yeah, I've lost track of time, so even regardless of the calendar.
No, but there has been
yeah, right.
Yeah.
Yeah, this year I don't know why there is confusion. It's been a lot of
Yeah, your voice is breaking.
Yeah, no problem.
Probably my connection.
Okay, thanks a lot.
So sorry for all the disruptions that came due to my poor connection. I'm trying to get a formal internet connection here, but it will take a while because I've moved to a new place. So I'm still depending on the hotspot of a mobile, which is pretty vulnerable.
But it